What I have here is a Denso Coil On Plug, part number 129700-4800 with a subcode of J0480. I can't quite make out the date of manufacture. It's not too important, I don't think. So yeah, this is a coil on plug. You have your high voltage end and two wires. So the first thing that comes to mind is how does this work? Is there active electronics in there? Is there serial communication coming across here? We don't know any of these things about it. I'm not too inclined to think that it's too advanced. It's probably just a coil, but there might be a flyback diode in there. Not really sure. There might be some coupling capacitors. Not too sure about that. So how do we determine that? Well, normally I just cut the damn thing open, but I'm going to try to determine it with instrumentation first. So the first thing I'm going to do is try to eliminate any possibilities of active electronics inside here. That is semiconductors. Okay, so I'm going to mount the camera on a tripod and go about that quick and dirty test. I'm going to use the Fluke Model 77. This guy's old, but I've been using it over 20 years. I know it very well. I know its quirks. So anytime you're doing something like this, make sure that you use instrumentation that you know very well. Okay, time to mount the camera. Okay, so here you see the old 77 facing you. We are in diode continuity mode, and reference position here, the 2-pin connector. We're just going to label these left and right, and then obviously we'll call this spark. Okay, so left, right, spark. So to help eliminate any possibilities of semiconductors in here, we put this into diode and continuity mode, because with this particular meter it can source about 2.5 volts of forward potential and about a milliamp, which is pretty good for a meter. You can pretty much get back to mid 80s semiconductors, maybe even late 70s, but a forward bias. I mean, it covers a wide range. So I do have a fair degree of trust in this particular meter for the test that I'm doing right now, but it's not an absolute. So we're going to start with the left pin, and I'm just going to put black on there, just arbitrary. That's where I'm starting, and red on the right. Okay, so we see now that we have voltage of 1 millivolt, and I'm going to go to the high voltage. Okay, 1.9. Likewise, black is still on left, red is on high voltage. Now I'm going to go black to left. 0.938. 0.938. So far, no signs of semiconductor. Now I'm going to swap the polarities of everything. Red is going on left, black on right. Okay, we see 0.1. Now black is on the spark, and red is still on the left. 0.938. Now red is on the right terminal. 938. Okay, I don't see any signs of a semiconductor in there yet. There could be some type of specialized high voltage circuitry in there. I don't know yet. But so far it looks good. This coil on plug is suggesting it's probably just a straight forward coil. Okay, so we're going to do the ohm test, and anytime we do something with a coil like this is pretty low impedance, so always short your leads out, get your lead resistance, 200 milliohm. That's 1 to 2. It's not the best for a meter, but I mean, you consider this is a portable meter. This thing gets beat around, it gets took out in the environment, leads are bent all over the place. You can't expect too much from it. Okay, so we're going to start left pin, black terminal, right pin, red terminal. Okay, 1.3 ohms. And again, we had 0.2, 0.1, so we're like 1.1, 1.2 ohm across there. And now we will go to the, I'm just going to arbitrarily throw black lead onto the left terminal, red lead on the spark, and so we're looking at 13K. So, okay, 13K. We're going to take black over to the right terminal. About the same, 13K. So I don't see any signs of any solid state circuits in this coil. So I'm good to move on to the next step. And what I want to do is just have a verification. So I'm going to move up to the benchtop Fluke, which has a lot better test leads on it. This is actually a 4-wire mode instrument, but it's only running in 2-wire mode right now. So we're going to go down to K ohm, 2-wire, 200 ohm scale. And again, I'm looking at primary right now. Red on left, black on right. 1.4, and of course I forgot to show lead resistance. Okay, lead resistance is 50 to 60 milliohm. A little bit better than the other. About a factor 10, a little better. So, 50 to 60 milliohm. We're looking at about 1.3 ohm. We're using a different meter. I'm going to swap the black to left, red to right, just to make sure there's nothing major going on here. I see a little bit different results now. Okay, there we go. So that was probably just contact resistance. Okay, so 1.3. So we're looking at about 1.3 ohms right now. So you just jot that down on your paper somewhere. 1.3 ohm. Now, I'm still not thoroughly convinced that we're at 1.3 ohms, so we're going to do some finite DC analysis on this. And to do that, we just need a voltmeter. Well, not a voltmeter, we need a power supply with a programmable current differential. So, okay, our current's already set at 1 amp. Voltage is down to nothing. Get out your probes, and again we are going red on the left and black to the right. If I can hold that on there. Now, being that this is a coil, I don't want to just jam the voltage at it, because we can get some flyback and some things can go and cause some hysteresis and control circuit of the power supply. So what we want to do is approach 1 amp. Which may be difficult. Okay. So now that it's set, I can see that we have 1.73 volts to get 1 amp. Now, Ohm's law is 1 volt through the potential. 1 volt potential through a resistance of 1 ohm will yield 1 amp. So this immediately tells us that I have 1.73 ohms of resistance DC analysis across this coil. Now, immediately we wonder where's the difference, because the other instrumentation said 1.3 ohms. Well, that was because I didn't zero out my probe. Here's my probe end. So we're getting about 0.47. So we're looking at 1.32, which corresponds quite nicely with the other two instruments. So DC analysis yields 1.32 ohm. When in doubt, always go to DC analysis. Unless, of course, you don't have DC analysis. For example, a switched mode power supply, such as we just got this guy right here, you're gonna have a very difficult time getting DC analysis because the output filter really sucks, especially in that particular power supply. So it's best to go with a linear model like this guy over here. It's nice. Okay, so we're fairly confident that we have 1.3 ohms on the input coil. So the next step then is to determine the inductance, and with that I have my high precision LCR meter here. It's the 4274A multi-frequency LCR meter. And now I do want to scan as low as possible because this coil is a low frequency device. So I don't know if we can see. Oscillator right now is at 100 hertz. It's as low as I can go. And we're in parallel mode. And we want to get inductance. So, first thing, we just want to make sure that our leads themselves have been properly zeroed. Okay, it looks like maybe some temperature effects, so we're gonna recalibrate the short circuit condition. Okay, it looks a little better. About 500 nanohenries is fluctuation, which you can't expect too much with cheesy alligator clips. Okay, so now we can check the inductance of the coil. Again, just to make sure there's nothing going on, we're going to go red to left, black to right, and then we're going to swap them. Okay, so we're seeing about 4.77 millihenry at 100 hertz. Now, I plan to run about a kilohertz, so I'm going to actually go up through here with a couple steps. And then want 20 hertz. 4.40 millihenry, 120, 200 hertz, 3.846 millihenry, 200, 400 hertz, 3.602 at 400 hertz. And I believe the next step is 1 kilohertz. Yes, 1 kilohertz. 3.54 at 1 kilohertz. Okay. Now while we're at it, we're going to keep this in parallel mode. And we're starting an internal trigger, high resolution. And I'm going to look at resistance just to get an idea. We're going to go down to 100 hertz now. Keep in mind that this is a reactive device, so we're going to see different resistance readings here because we are testing at 100 hertz, not DC. So, likewise, at 100 hertz, we see 4.96. Okay, 4.96 resistance. Now, we know that at DC we have 1.3, so we should be about 5.8 to 6 ohms impedance. This is just guessing. Okay, so we got some capacitive action going on here. Okay, so we definitely know that there's some capacitive action going on in the probably the secondary. So there might be a capacitive filter in there, or it could just be that there's 13 k ohm of winding that are acting as a capacitor. This is just a good general ballpark figure to have. So let's just look at 1 kilohertz. Let's see what the resistance is. Oh, we're up at 197. Yeah, so we definitely know there's some passive action going on. Okay, I'm going to lead towards, this is all just straight capacitance from the secondary winding. Okay, I don't think I need any more numbers from this guy. And no, I don't think we do. Okay, we're going to make a circuit and test this coil. And that will be next. As it turns out, I wasn't done. Show you what I need. Here's our rough ball schematic of our coil on plug. So we have a primary, which we know is 1.3 ohms. We have a secondary, which is 13K. We know the secondary is the high voltage, so we can label that. However, the 2 pins, we don't know which way they go. Now the difficulty arises in the fact that this is 1.3 ohm and this is 13K. So we're going to need some very high precision measurements to be able to take the decimal point out to measure between B and A and C and subtract the difference. They probably make instruments that do that. I'm not aware of them. The easiest way that I know to do it is take an inductive measurement on both sides and then take the difference. Now this assumes common dot notation, which would be, this is arranged with both dots would be on top. If the coil's not arranged in common dot notation, we're right back to square one. So we do have to make some assumptions here. So I'm going to get the inductance readings to the coil here, high voltage side. So I'm going from the left pin, which the left pin doesn't have anything yet, to the high voltage. Okay, so left pin to high voltage is, let me write this down, left to high voltage, 18 Henry. Right pin to high voltage, 18.25 Henry. So we see there's definitely a difference, but without knowing for sure of the dot notation, we still can't be sure, and it's a gamble. I'm going to assume dot notation. So 18.22 Henry. Okay. So with that notion, I'm going to say that the right pin is A, and the left pin is B. Let me see if this is right. Okay. So here, I filled in the blanks, and I'm going to say based on this that the left pin to high voltage was 18 Henrys, which implies a fair amount of windings, but not as much as 18.22. Again, common dot notation. Okay, so the right pin should have more windings, which would be A, which should make sense because there's going to be more windings coming down from the primary and adding on top of the second. Now again, assuming dot notation. I'll put the dots up here. This always assumes common dot notation. Now if one of the dots are reversed, which it's very likely, we got the opposite results, but we just got to start somewhere. So with this notion, what did I do here? Okay, so I had B in there twice. There's C. So here we can see it now. The question comes of, how do we drive the coil? There's a number of ways you can drive it. Let's see, I'm going to pause this quick while I sketch something up. Okay. Old school method might be to say we're just going to pulse a 12 volt line. We're going to ground the center and just going to let that work. Okay. Well, that would probably work. Other than we're going to have a ring back and we have to find a control device to pulse the 12 volts. Now, semiconductors do not like working with positive voltage because in physics, positive are actually holes. And it's more difficult to switch holes than it is to move electrons. Electrons are a negative charge. So this particular arrangement would dictate for a PNP type device. You could use an NPN on here with some bases swapped around, but we're just keeping the basics here. So we need a PNP device, which would mean we need a lot more silicon area to perform the same thing. Costs are going to be higher, there's going to be more heat dissipation, efficiency is going to be lower, so we don't want to go with this route. Let's scratch something else out. Okay, another way. We feed 12 volt to the primary, and we switch the common point, which would let the EMF fly back. Now the problem with this is, now we need a diode, which almost all devices are going to have this. We got to figure out what type of topology we want to use here, because the ring back is going to be adding, and we're going to get a potential across this difference here. So we might have 12 to 15 volt flyback in this particular area, maybe a little bit more, and that's it's somewhat questionable, and we're probably going to need a pretty heavy diode. Although this method is easier, I don't like the virtual grounding that it opposes, so let's see if we can find something else. Okay, here's another thing I scratched up. We swapped the schematic around a little bit, and now we're feeding the 12 volt to the common portion, and we're going to switch the primary. Again, we still have your ring diode. I haven't decided what type of switch to use. This particular arrangement has the advantage that the flyback is not going to induce much voltage here, but rather it's going to add to the battery. So the high voltage actually turns into a boost mode, adds to the battery, so the battery becomes part of the virtual circuit to ground. The only problem with this approach is, under high RPM, high frequency, if the battery were to suddenly become disconnected right in the middle of a pulse, this would open up in free will and it allowed all of the energy to come back through this portion and likely damage these electronics and anything else that might be on a 12 volt, but I am guessing that's probably how the manufacturer does it, being that I've heard reports of ignition systems failing by pulling the battery while the engine was running. So that's definitely not a characteristic we want, but everything else seems to be in order, and this is the way I'm going to go, at least until I see reasons otherwise. Okay, let's build a circuit. Okay, here's what I come up with. This was just parts I'd laid actually on the bench, which was a QFET. Now this is not ideal, I would not use this in application, but it's good for bench test. You see it's only a 60 volt rating. I'd like to see, oh boy, with a 40 volt boost mode, I'd realistically 150, 200 volts on this guy. But this will work for this test. So I have two of those QFETs in parallel mode. There is a, you see that resistor there, that's just a 500 ohm gate discharge resistor, just to get the capacitance off the gate for switching frequency, which probably 500 volts. 500 ohm is a little excessive for this application, being it's only going to run 1 kilohertz. There's a little electrolytic 0.1 microfarad capacitor. Electrolytic is not ideal for this application, but it's good enough, and actually 0.1 microfarad is not quite right for the balance of the inductance, but it's stuff I just had laying around. It was the closest stuff I could find, then, you know, rules of thumbs and common sense and all that good stuff. So we have all of this wired just like I showed in the schema before. So here's the red coming through. Red comes down to the where's that? Oh boy. Let's see. We have these labeled somewhere. C. So we call where red goes in would be called C. And we can see that it's the following the layout that I had shown before. 12 volt goes into it. So 12 volt goes into C, which is the red, goes down here. And I just didn't feel like using another alligator clip, so I jumped it over to ground. So it's actually 12 volts, or it's whatever the supply voltage is subtracted would be the difference in a real world application, which isn't negligible for this because it's high voltage. And our A terminal, which would be the portion where the switch is here. You see A on this side, which is the primary, comes back to the switching circuit, which is parallel resonance with a 0.1 microfarad capacitor. The gate comes out to the yellow, and this pin right here is from the frequency generator out. I have it in sweep mode right now. You see 9, and we are on square wave. You can see sweep, 9 volts. We'll go to the menu here. Start frequency. Oh boy, how do I use this menu? Start frequency is 400 hertz. Stop frequency 1 kilohertz. Sweep time 500 millisecond, half a second. Okay, so that's probably pretty much ideal for my driver. I'm sweeping 400 hertz to 1 kilohertz and 500 milliseconds, and that would be the carrier. And we have this jumped over to a counter to show me how many pulses I get. And here's my power supply. So I'm going to start with 12 volt, and we're going to we'll focus here. Okay. You can hear the sweep. I'm going to mount the camera here and throw some more current and pulse at it. I didn't show the duty cycle. We're at 50% duty. Okay. We're going to mount here and do some more tests. Okay, there you can see the spark plug in the middle of your screen. I'm going to back the duty cycle off to 20. Reset the counter. Okay, we can hear the spark going out there. I'm going to increase the voltage now. Here's 20 volts. Still not good at 20%. 30 volt. 40 volt. Okay. Now I'm going to take the duty cycle up to 50. This will give it some serious power. That is 50%. That was 22,000 pulses. Let's just give it a little bit more, which is going to be overkill at 40 volts. Go up to 80%. Which we didn't really hear much of a difference. There's probably not much of a reason to go beyond 50%. Even at 50%, my power supply is kicking out at 5 amp at 40 volt. Okay, so what are we doing here? Go back to duty. 30%. So we probably don't need to get much higher than 30%. Not just me flicking the wire. Okay, I don't see any problem driving this these coil on plugs. Everything looks fairly straightforward. So I think I'm going to move on to the next step, and that would be triggering this from the CDI. It's going to take a lot more than that. I'm going to have to build a circuit, but hopefully that helped somebody.